We're starting in Chapter 6 dealing with antiderivatives, and this is a completely new concept than what we've been doing. However, it's very similar, it's just in the opposite direction. Definition, let's start off with that. Suppose that f of x is a given function and that capital F of x is a function having f of x, little f of x as its derivative, that is f primed, big F primed of x equals little f of x. We call big F of x the antiderivative of little f of x. So in other words, we're basically wanting to work backwards in this section from what we're used to. We're used to starting with a function and taking its derivative. Basically what we're going to be doing is we're going to be starting with the derivative and then working backwards to get the original function. Now, please realize that this is a little bit different because antiderivatives are not unique. Okay? What does that mean? Well, let's look at little f of x as x squared minus 2x plus 1. We're used to the fact that if we take the derivative of little f of x, we get f prime of x is 2x minus 2. Well, if I look at another f of x, say little f of x is x squared minus 2x minus 8, this derivative is also f prime of x is 2x minus 2. So going forward, if I take the derivative of the function, I'm always going to get the same answer. Okay? However, remember, antiderivatives work backwards. So the question is, when I work backwards, how do I know which one of these to pick? And we're going to sit there and talk about the general form of an antiderivative, what's called an indefinite integral. We're going to get into that in a second. We do need to use new notation, okay? So the new notation we're going to use is what's called the integral sign. It looks like this really long, elongated s. So the integral of little f of x dx is equal to the big F of x. Remember, the derivative of big F was little f, so the integral of little f is big F. Some basic antiderivative rules. These are things that shouldn't come as a surprise. If I take the integral of two separate functions, the integral of f of x plus g of x, this is equal to the integral of f of x plus the integral of g of x. This is just like our derivative when we took the derivative of multiple functions. We just split it up and took the derivative of each piece individually. Similarly, if I have a constant times a function, the integral of a constant times a function, I can bring the constant out and then multiply it by the integral of the function. Now let's start working on the real rules that we're going to be focusing on here with our antiderivatives. The antiderivative of your power rule, the integral of x to the r. So here's my base x. I have some exponent. This integral is 1 over r plus 1 raised to times x raised to the r plus 1 power plus c. Let's just talk about this piece here first. Okay? This should make sense because if you remember, you take your derivative, you take your number in the exponent, multiply it by what's out front. So if I multiply the r plus 1 times this 1 over r plus 1, they cancel. And then I subtract 1 from my exponent. So r plus 1 minus 1 is just r. So if I take the derivative of this side, I should get what's inside the integral. And we do. Now the derivative of constant is just 0. The question is, why is this constant here? Okay? This allows us to understand that this is not unique. If you remember, I said briefly that an integral, an antiderivative, is not unique. And basically what we're doing when we take an integral is we're getting the class of all antiderivatives. So the antiderivatives that look like this, when we take their derivative, we'll get this function inside. Again, we're just working backwards. We're doing the opposite of our power rule. So the integral of x to the r power is 1 over, in this case we add 1 instead of subtracting 1, and we divide it instead of multiply it. So 1 over r plus 1, x to the r plus 1 plus c. Let's see some examples of how this works. Integral of x to the 5th dx. Well, this is our rule. Integral of x to the r dx is 1 over r plus 1, x to the r plus 1 plus c. So my r, in this case, is 5. So my integral is just 1 over 6, because that's 5 plus 1, x to the 6th plus c. Again, we should be able to take this right-hand side, take its derivative, and wind up with what's inside. And we are able to do that, because 6 times 1 6 is just 1. Subtract 1, we get x to the 5th, and then the derivative of a constant is just 0. So again, the integral is just working backwards. Our next example, 3x to the 8th. Again, this is a power rule. However, we need to remember our rule, which says we have a constant, and when we have a constant inside, we just bring it out. So really what we just want to focus on is the integral of x to the 8th. This is x to the r in this case is 8. So I want to add 1 to that. So this is going to be the 3 bringing outside. Add 1 to the 8, I get 9. So this is 1 over 9, x to the 9th. Now we do need to simplify this. We're still going to add our c. We need to distribute this 3, and we get 1/3 x to the 9th plus c. Again, this isn't very difficult. It's just following the rules, but all your rules are backwards. They're basically the inverse of what we've been doing to date. This is a little bit different because I have a constant. What is the integral of a constant? Well, we knew the derivative of a constant was 0, but we're going the opposite direction now. This is actually still our power rule, but we don't see an x. However, we want to think about it. This is really 4 times x to the 0 power, because anything to the 0 power is just 1. So if I think of it as x to the 0, okay, then I add 1 to it. This is going to be 1 over 1 x to the first. Again, I'm going to factor the 4 out. And this just becomes 4x plus c. Again, if I take my final answer and take the derivative, I should wind up with what's inside, and we clearly do. Our last example of the power rule, I apologize for not going up slowly with it, but this is just taking the integral of multiple terms. And if I take the integral of multiple terms, this is just taking the integral of each piece separately. What I want to do here, though, is notice I have 1 over 6x squared. I want to rewrite this as x to the negative 2. This will allow me to apply my power rule. Take the integral of x, it's 1/2 x squared. Again, we're just adding 1 to the exponent and then dividing. Minus 3x to the 4th, the integral of this. Add 1 to the exponent, I get 5, so minus 3/5 x to the 5th. I'm going to pull the 1/6 out. I'm going to add 1. Again, this is the part we got to worry about. Add 1 to this. Negative 1, 2 plus 1 is negative 1, so it's 1 over negative 1. X to the negative 1. And then it's just simplifying. 1/2 x squared minus 3/5 x to the 5th plus 1 over 6x plus c. Again, if we take the derivative of our final answer, we will get what's inside. And there's our rule there. We got a couple more rules we got to go over, and then we're going to hit some word problems. The integral of e to the kx, this is simply 1 over k e to the kx plus c. And once again, just like our power rule, if we take the derivative of the right-hand side, we'll get the stuff inside. The derivative constant is 0. Derivative of e to the u is e to the u du. So this is e to the kx times k, and the k and the 1 over k will cancel. So this should make sense that this is our antiderivative. And the derivative of 1 over x is natural log of the absolute value of x, because we do know the derivative of the natural log is 1 over x. So, here's some examples. Integral of e to the 9x. We know our rule is e to the kx dx is 1 over k e to the kx. K in this case is 9, so this is just 1/9 e to the 9x plus c. Similarly, the integral of 8 over x dx. Again, 8 is just a constant I can pull out, so this is 8 times the integral of 1 over x. So the integral of 1 over x is the natural log of the absolute value of x. So 8 times the natural log of the absolute value of x plus c. And again, we use the absolute value because we know we cannot take the natural log of a negative number. Can we figure out c? We've been using this plus c. The question is, what is it really? Can we ever actually figure out what c is? If we actually know a point for the antiderivative, we can. We can integrate, then plug in that point to solve for c. Let's look at an example. Find all solutions f of x with the following properties. F prime of x equals x to the 12th. F of 0 equals 9. So I'm given the derivative, and I'm given a point in the antiderivative. So what I want to do is start with the original function, start with the derivative of the f prime of x, and take the antiderivative. So the integral of x to the 12th dx is 1 over 13 x to the 13th plus c. Now notice what I said. I said if I give you a point in the antiderivative, which is what we have, the point is 0, 9, we're actually going to plug in. So I know that the antiderivative is 1 over 13 x to the 13th plus c. So f of x is equal to this. Plug in the point 0, 9. Well, f of x becomes 9, Plug in 0 for x. Well, this 1 over 13, 0 to 13 is just 0. So this gives us c equals 9. So now I'm going to take this original function, this function I was calculating the antiderivative. I'm going to take the fact that c equals 9, and my answer is simply going to be f of x is 1 over 13, x to the 13th plus 9. Let's look at a couple applications of this, because this is really what we're getting at with this section. A ball is thrown upward from a height of 432 feet above the ground. I should say ground, not grown. With an initial velocity of 92 feet per second. From physics, it's known that at time t, its velocity as v of t is 96 minus 32 feet per second. Find s of t, the function giving the height of the ball. Well, what's really nice about this is we were already given situations like this where we're given the position of the ball, the height of the ball, and we took the derivative to get the velocity. So the opposite holds. We know the derivative of the position function is velocity, so we can integrate the velocity to get the position. So let's take our velocity function. V of t is 96 minus 32t, and let's take the integral of that. The integral of 96 minus 32t is 96t minus 16t squared. Of course, we're just doing this in one step. We know we add 2. We add 1 to the exponent, so this becomes t squared, and then we divide, so 32 divided by 2 is 16. So now this is our position function here. Well, notice what we said already. A ball is thrown upward from a height of 432 feet above the ground. This is our initial position. So at time 0, we know the height is 432. This is the point that we're actually given. So we're going to plug into this position formula. 432 is the position at time 0, and this gives us c is 432. So just like we did on the previous problem, we're going to take these two, this equation and this constant, knowing that c is 432, and this is going to give us our new function. S of t is 96t minus 16t squared plus 432. Let's look at one more example. A yo-yo store finds that at sales levels of X yo-yos per day, its marginal profit is M of P of X dollars per yo-yo, where the marginal profit is equal to 1.70 plus 0.18x minus 0.009x squared. Also, the shop will lose $65 per day at a sales level of X equals 0. Find the profit from operating the shop at sales level of X yo-yos per day. Again, we know certain things about this. We know that the derivative of the profit function is the marginal profit. We always got marginal profit by taking the derivative of the profit. So if we work backwards, if we integrate the marginal profit, we should be able to get the profit function. And that's what we want to do, is find the profit function. So let's look at this again. I'm going to integrate the marginal profit. The integral of 1.7 plus 0.18x minus 0.0009x squared. All we're going to do, integrate each piece separately. So this is 1.7x plus 0. This should say 0.09. I'm going to pause and fix it. There we go. Integrate each piece. This is 1.7x plus 0.09x squared minus 0.003x cubed plus c. This is now my profit function, P of x. And I know P of x, I'm going to plug in negative 65, because I know if I sell 0 items in a day, I'm going to lose $65. So my profit's negative 65. I plug in 0 for all your x's, and again, this leads us to c is negative 65. So therefore, our profit function is just combining these two, the integral, which is a class of all antiderivatives, finding out what c is equal to, and then getting the specific profit function for that store. So P of x is 1.70x plus 0.09x squared minus 0.003x cubed minus 65.